So, let us get started where we left off in the previous class, and because we are going to do the tutorial and the next lecture, I have just changed the plan for the today's lecture a little bit. We will actually focus on solving a few problems, so that you are ready for the tutorial as well as your assignment. Okay. So, this is where we left off. So, let us say the reaction is AA giving B, okay, and you are given that the rate of progress of reaction as it is written is KCA to the power say 1.2. Okay. Go ahead, spend 10 minutes or so to design the CSTR. Okay, whatever approach you want to use, you can use it. Okay. Those of you who don't know or who are not from chemical engineering background, take the overall balance equation for CSTR, where left hand side will be 0 because d by dt is going to be 0, and then move things around so that you can calculate V. Okay. So, question is given requirement of let us say X target or something else. Again, I am saying X target because that is how in undergraduate this problem is formulated. So, given a requirement that X A should be equal to some X target, what should be the volume of the reactor? Hey, please feel free to talk to each other. If you have done solving the problem, you can just move around, help each other as well. And assume it's liquid phase, that means Q, volumetric flow rate is constant, V is constant. So, yeah. And you can assume these to be known also. Okay, let us do this. Okay, and again there isn't necessarily one way of doing this, but this is a way. So, 0, now that is liquid phase. So, we will have Q C A in minus Q C A, okay, plus nu A R, okay, which is nothing but minus A K C A to the power 1.2. Okay. Oh, sorry, R A V, I forgot the V, right. So, we can take this guy on to the left hand side, and you will have V multiplied by A K Ca to the power 1.2 is Q Ca in minus Ca, and you divide throughout, you are going to get this as A okay. If target Ca is given, you know Ca in, you input your target Ca, you will get the solution. If target Xa is given, then we just have Xa is nothing but Fa in minus Fa out divided by Fa in, which is Q Ca in minus Ca divided by Ca in, and then this gets cancelled. Okay. Xa is not equal to Ca in minus Ca divided by Ca in. Okay. Xa is that particular value only under a specific condition. What is it? If Qa does not change. An example would be liquid phase reaction, another example would be gas phase reactions without change in number of moles. Okay. It non-isothermal gas phase reaction will not be a case where this is valid. Gas phase reactions of the nature of ammonia decomposition, ammonia synthesis, let us say reforming reactions that we considered so far, there will not be examples where this is valid, but water gas shift would be an example where this is valid, because you have two molecules reacting, two molecules giving products. So, change in number of moles because of reaction is 0. Okay. And therefore, you will be able to write Ca equals Ca in Xa, right, minus Ca in, which then can become Ca is negative, sorry, Ca in 1 minus Xa. Okay. Again, these are things that you know how to do. So, I will just put this over here like this. Okay. Now, if you look at this, if you just rearrange all of this, it's you will be able to get the expression in blue in a very straightforward manner. Okay. Some of you from your undergraduate, you might be used to writing V equal to okay, and then you might be tempted to write no, that is not there, you need to have your A also. Right. Remember the definition of RA that was used in your undergraduate. Okay. Lot of standard problems in undergraduates are already reformulated for you in terms of A giving products rather than small a giving products. So, if you have confusion, that confusion stems from there. You can go back to your undergrad college and tell them that you have let me utterly confused. Okay. You can't come to me and say that in my college I was taught something wrong. So, you can always come and say that, of course, not a problem. Then we will discuss and we will try to iron out those issues. Okay. So, that is what the next slides have is overall balance. Since Fk equal to Qck, we get this, therefore V is this, that is the left hand side, that is what we have done. Using design equation, we can write, and this is I find a better way of writing this is, if you have Fa naught, again I should not have used Fa naught. Okay. Yeah, so this is what essentially you will get. Ca we had written over here, Ca is Can multiplied by 1 minus Xa, and therefore Ca to the power alpha is same as Can to the power alpha multiplied by 1 minus Xa to the power alpha. Okay. These two are exactly the same. Okay. Yeah, questions, confusions, another way of solving if you have. Okay. The balance that you see on the left hand side is, yeah, sorry, just I will finish this. Balance that you see on the left hand side is nothing but dnk by dna by dt equal to fan minus fa plus rav, dna by dt equal to 0 because it is a steady state CSTR. Yeah, sorry, you had a question? Why you did? Okay, the question is, where did the term xa come from in the right hand side? So, where did the term xa came from is it's come from problem definition. Okay. So, if the problem is given as find the volume such that you meet a desired xa target. Okay. So, then the desired xa is given to you and you have to compute volume based on that. Now, rate of reaction or rate of progress of reaction is okay. So, strictly speaking, I should not have written that as R xa. Strictly speaking, I should have written it as something like R bar xa. Why? What does R of xa mean? R of xa means you take the value of xa and plug it into k Ca to the power alpha. So, R of xa technically means, let us say concentration, inlet concentration was 5 and we say there is 50% conversion, outlet concentration is 2.5. So, R of 2.5 means you put k multiplied by 2.5 to the power 1.2. R of xa will be R of 0.5. So, R of 0.5 means k multiplied by 0.5 to the power alpha. So, what she has said is strictly speaking, it is absolutely right. I should have used a different function notation for that, right. So, just the mathematics, simple mathematic nomenclature, if you have f of x, okay, and you put f of 2.2, what does that mean? Wherever x appears, you are replacing it with 2.2, okay. Likewise, if I call this as f of y, this actually does not become a different function, it just means f of x where all places where x appears are replaced by y, Okay. So, strictly speaking, if I were to follow the strict mathematical notation, R of X A basically means I would have just replaced C A with X A, but that is not how we do. Okay. So, we are going to use a little bit of abuse of notations simply because I do not want to keep introducing more and more notations. Okay. So, when I say R of C A, what I mean is rate expression where C A, so R equal to K C A to the power alpha is what R of C A I would mean. When I say R of X A, I basically means you can replace C A with an expression that depends on X A. So, I should have written that as R of C A X A or R bar of X A. This is the strict notations. Okay, but we are going to use some abuse of notations for simplicity of understanding. So, we will use the context a little bit. Likewise, you know, when we write mu kj, okay, in our minds somehow by the end of this course you will think you will associate k with species and j with reaction. That is not how it works. Mathematics, the first subscript is the species subscript, second subscript is the reaction subscript. So, if you mix that up, yeah, that it doesn't work, but we will try in the entire course not to ever use J for reactant and K for species, K for reaction. I will always use K for species, I will always use J for reaction, and I will be a loose body that can either replace J or it can replace K as the requirement might be. Okay. Again, if you are not necessarily very strong at mathematical notations, you do not have to worry about the discussion over the last 4 minutes. Okay. So, that is that about how to use the reaction rate. Okay. Let us talk about elementary reaction. So, let us say if we had instead of AA giving products, let us say we had 2A reversibly giving B. We saw that example yesterday, right? NO2, 2 molecules of NO2 gives a molecule of N2O4. That was an elementary reaction. Because it was an elementary reaction, our R forward was K forward Ca squared, R backward was K backward Cb, okay, and R net was equal to the difference between the two, which we can write as K forward Ca squared okay. This is what you have learnt. Okay. How does this come about, or what is the implication of this? The implication of this is at equilibrium, okay, at equilibrium rate of forward reaction is equal to rate of backward reaction, okay, which means Kf Ca squared is Kb Cb, okay, which will yield us which we write as Kc, okay. The other consequence of what happens at equilibrium is that this term becomes 0 at equilibrium. Okay. So, reversible reactions often can be written as, not often, can always be written as a forward reaction term multiplied by 1 minus product of concentrations to the power the stoichiometric coefficient divided by Kc. Okay, that is what we ended off with in the previous class. Okay. Again, these are concepts that as chemists you would have learnt in thermodynamics course, in your first year thermodynamics course also you would have learnt, and would have reiterated them in thermodynamics as well as CRE. Okay. Nothing new. Okay. Now, the other thing is, how is this related to delta G naught of reaction? And the thing that you would want to remember is K equilibrium is e to the power okay. Is K equilibrium equal to Kc, Kp, Kx? What is K equilibrium equal to? Let us again take the same reaction 2A going to B, and let us say that the reaction is at equilibrium. What is Kc equal to? What is Kp equal to? What is Kx equal to? Yeah, you can write it down in your books. Again, simple concepts. I was a student, I kept confusing them. Okay. When I have taught this course for 6 times now, I have seen more than half the class confuses them. So, that confusion is normal, because in our undergraduate equilibrium is taught in a different course and reaction rates are taught in a different course. So, now when you have to look at reversible reactions more often, that confusion is there. So, Kc, hopefully you have written that as Cb Ca squared, Kp is partial pressure of B divided by partial pressure of A squared, and Kx Xb divided by Xa squared. Okay, I have just put EQs so that later on when you come and look at this, you do not get confused, because there is already, I have already put equilibrium before, but just to be clear, okay, these are the values at EQ. So, what is this K equilibrium equal to? Is it Kc, is it Kp, is it Kx, or is it something else? Kc, what else? K equilibrium is ratio of activities. Okay. We will assume in this course all mixtures to be ideal mixtures. So, ideal gases, ideal gas mixtures. If it is liquid, they are ideal liquids, that means volumes do not change, okay, and ideal mixtures. Okay. Ideal mixtures would mean fugacity coefficient equal to 1, activity coefficient equal to 1. Okay. If that is the case, then the shortcut is K equilibrium is equal to Kx when we are talking about solids, it is equal to Kc when we are talking about liquids, is equal to Kp where pressure is in bar when we are talking about gases. Okay. This is just a shortcut. These are not the correct definitions. This is just a shortcut. The correct definition is based on activities. Okay. Activity in solids is based on how much amount of that particular material is there in fractional terms. In liquids, it's a little bit complicated, but it's not complicated, but let's use concentration as a shortcut to K equilibrium. And in gases, the standard state is 1 bar at 298 Kelvin. So therefore, your Kp is going to be P by P hash, and P hash is 1 bar. So if the pressure is 2 bar, activity is 2, or P by P naught is 2. If pressure is 5 bar, P by P naught is 5, and so on. Okay. Just that particular value is dimensionless when we are talking about K equilibrium. When we are talking about Kp, it is bar. So again, as I said, shortcuts, right? They are not equal. The numbers are equal for the purpose of this course, and I cannot stress this enough, for the purpose of this course, because you are going to encounter situations where some things in some minor way is violated, and then don't come back to me. And if you watch Ranveer Varar videos, don't come back to me and say Ranveer ne bataya nahi tha. So I have told you that these are all shortcuts. So you don't watch YouTube videos of Ranveer Varar. Okay, he's a chef. Okay, so K equilibrium equal to Kc for liquids, Kp for gases, Kx for solids, where concentration is in moles per liter for liquids, is in bar for gases, is mole fractions for solids. These are shortcuts, they are not equal. Kc, Kp, Kx are dimensional quantities, K equilibrium is non-dimensional quantity. Okay. All right. Yeah. And that's what rest of these slides say. Okay. Now, if we have a case where order of reaction is not equal to molecularity, okay. So let's take the other reaction we have been looking at. Let's say this was 2A going to B and not the N2O4 reaction, let's say some other which was non-elementary reaction, and our rate of forward was Kca to the power 1.2. What do you think rate of backward would be? Or yeah, rate of backward, it will be Kcb to the power 1. Anyone? You are thinking, if it was Kcb to the power 1, it would not have been on the slides, right? Don't think like that. Okay, this is, sorry, yes, 0.6. Why did she say 0.6? Yes, very good attempt. I like the attempt. I wish it was 0.6. My life to explain everything would have been easier, but no, unfortunately, it's not 0.6. Okay, keep in mind that at equilibrium, rate of forward should be equal to rate of backward. Okay, at and that is valid irrespective of what the concentrations are, what the temperature are, what the pressure are. Okay. Other hint is, in all your rate expression, your K terms do not depend on concentration. Okay. So use that in the next class, that's in our tutorial class. I'll have a small discussion before we start the tutorial. Okay. So we'll leave this suspense, right? Just like all thriller TV series. I don't watch too much TV, so I don't know, but they will end up with suspense at the end. So this is the suspense at the end. Well, the suspense is solved, but you know, okay. We will take this example, or we will take the some other example before. Okay. Let's take this example. Easier. Okay. Consider these three reactions. Now, everyone over here is expected to know that enthalpies, entropy, free energies are state function. Okay. What that means, we will come to that. Expected to know does not mean that you will immediately know. So, let us try it out. In your books, you can talk to each other. What is delta H3? In the unrecorded class, I used to have a poll where you can type the answers, but because this is being recorded. Yes? Minus 90? How do you get that? Is you see that the last reaction is first minus second reaction. Okay. So, we will have CO2 will have plus 3H2, okay, will go to, okay, or can have 1 H2 and go to CO and will go to CH3OH. Okay, it needs to be balanced. Here I'm not, you know, putting this out. I mean, you need to have this balanced out. Okay, but we are just for simplicity we are just showing this. Okay, what does state function mean? State function means that your delta H's or delta S or delta G or delta A or whatever is the state functions are dependent on only the start and the end point. They are independent of the path taken, okay, which basically means this is delta H1 . Yeah, sorry, these notations are too small over here, but it's okay. Delta H1 is equal to delta H2 plus delta H3. Why? Because from that lower path, it's delta H2 to plus delta H3. Okay, and therefore delta H3 is nothing but delta H1 minus delta H2, and therefore delta H3 is minus 90. Okay. Now, the consequence of this also, and the same will work with delta G as well. Okay. So, therefore, you will basically have okay. Let us divide by RT and let us take it exponent. Okay. If we take exponent of this or divide by negative RT and take its exponent. If we take exponent of this, you will basically get e to the power minus delta G1 by RT equal to e to the power minus delta G2 by RT multiplied by e to the power minus delta G3 by RT. Okay. What are all of these? These are nothing but your K equilibrium. Okay. This is what it is. I do not know, I might have given a direct answer to one of your assignment problems. Maybe this was last year's assignment, I don't remember. Okay. And all of these things that I have discussed is all there, and the derivations and everything is all there in the rest of the slides, which by popular demand based on your feedback, you said please prefer to solve some more examples. So, I have preferred to solve examples rather than spend time on derivation. Okay. We still have 10 more minutes approximately, not 10 minutes, 7 minutes. Okay. And there we will solve one problem. You have okay. So, let us say this was done in either a constant volume reactor, constant pressure reactor, batch reactor, whatever the case might be. Okay. We are going to talk about how to approach these problems. In the tutorial, we will actually solve the problem. I am only going to talk about how to approach this problem. One more suspense. Too many suspenses in today's lecture. You can try a few steps out, so that is why I am giving a little bit of a pause, or keep your pens down and get ready for the next. For some of you who knows these things, this slow pace might be boring, okay, but this is intended for others to catch up. You can do some neck exercises, eye exercises, hopefully not running around in the class, but everything else. Okay, how do we approach this? Okay, the way I would recommend you would approach this, and again that is the way it is solved in Davis and Davis also, okay, is let us say we will start off with whether if it is a flow, then it is moles per time. If it is a batch system, then you start off with total number of moles, okay, any extensive quantity. Okay. So, initially let us say we have stoichiometric amount of CO and air. Okay. So, what does stoichiometric amount of CO and air mean? What would the composition of gas initially have? 1 mole CO. How many moles oxygen? 0.5. How many moles CO2? 0. Okay. Now, this is where notations gets confusing. You can go back time travel 100 years and you can tell them over here. The term stoichiometric amount of CO and air basically means that the reactants are in the ratio of their stoichiometric coefficient and products are not present. Okay. So, that is what stoichiometric amounts of reactants and products mean. Okay. What else will be there? Nitrogen, okay, because it is CO and air. Okay. How much will be nitrogen? 0. No, initial. Okay, 0.5 multiplied by 79 by 21. Okay, or 80 by 20. Yeah, we will do it 80 by 20. Okay, which is 4, which is 2.0. Okay. Okay. We will assume zeta 1 to be the extent of reaction. Remember, I had said that this is one place and one of the few places where we will use extent. Everywhere else it is actually more cumbersome to calculate the extent than it is. I mean, you can very well use it, okay, but yeah. it may not really help. So, if zeta 1 is the extent, the amount of each species that might be formed because of the reaction progressing by amount zeta 1 is going to be what? The stoichiometric coefficient multiplied by the extent. So, if zeta 1 is the extent, here we will have minus zeta 1, actually this is not zeta, this is chi, but chi, no, what? Psi, xi, minus, sorry, minus half zeta 1, this is plus zeta 1 and this is 0. Okay. Remember that we had Nk equal to okay. So, those of you who are mathematically inclined, you can use this. Those of you who like the feel of chemistry a bit more can use the table as we are writing. So, final is going to be 1 minus zeta 1 okay. So, these are the total number of moles. Okay. What happens at equilibrium? At equilibrium your Kx is given. If your Kx is given, that is equal to x CO2 divided by x CO, oops, right. Now, the total number of moles is 3.5 in the at the start, and at the end it's what, 3.5 minus 0.5 zeta 1. One point five? Yeah, 1 minus 1.5, right? Yeah, 0.5 zeta 1. Okay. So, from the moles and total moles, you can calculate x, plug it into that equation. That ratio is going to be equal to Kx. Solve it for zeta 1 and you will get the value of zeta 1. Okay. If you have 5 reactions, zeta 1, zeta 2, zeta 3, zeta 4, zeta 5. If you have million reactions, zeta 1 to zeta million. Okay. There are other ways to do this rather than zeta 1 to zeta million, and that is based on free energy minimization. So, if you look at softwares like Aspen Plus and so on, depending on number of species and number of reactions, they would either prefer free energy minimization or they would prefer this particular approach. Okay. Free energy minimization itself is an ongoing task. Even right now there are research papers on how to get the equilibrium conditions. It is not necessarily straightforward. We are taking examples where things are fairly straightforward. Even just a few months back there was a paper on CO2 utilization which delved into the economics of the equilibrium. This is again 2024 that we are talking about. Okay. So, all the things that you are learning are basically things that we have simplified in terms of 1 or 2 reactions, but the concepts are broader, and I am trying to give you the broad context by giving the mathematical expression. Okay, you can't go with your feel if you have 1000 reactions and 50 species. Okay, but that feel is very important. So the math and the chemistry both are really important for you to solve problems in a very efficient manner. Okay, if we have time, I will very quickly take some 15 minutes to talk about, if this was a large scale system. One of my collaborators in Korea is working on a reaction mechanism that has 54 reactions. That is very much in CO2 utilization space. So I won't talk about her exact reaction mechanism, but how all of these concepts that we are talking about, how they can be applied when you are talking of 18 species and 54 reactions. Okay. If we have time, I'll maybe take a 10-minute, 15-minute segue in the class after the tutorial. Next class will be the tutorial class. Okay. All right. Thanks everyone, and see you in the tutorial. Yes. Just to keep things simple. I didn't have time to incorporate. So the question was, why did we not incorporate the second reaction? I didn't want to rush things. We will do it in the tutorial. So this will be one of the tutorial problems. Okay. So shouldn't do it like this. I was saying that if there was only one reaction taking place, then what would happen? Okay. So this is not. We will solve this in tutorials. You will solve this in tutorial. Okay. You'll formulate the problem, and then we'll probably later on see ways to solve it. Okay. All right. Thank you, everyone.